Good morning, everybody. We'll get started here in about 2 to 3 minutes. Thanks for your patience. Thanks for joining in, everybody. We'll get started in about a minute. Thanks for your patience. All right, good morning, everybody. Thanks for joining in. If you weren't with us last week, welcome. And I'll be sharing some information today very quickly to try to bring everybody up to speed. So let me go ahead and share my screen. So you should be seeing now the course homepage. Am I correct?
Yes, ma'am.
Thank you very much. Let me make sure my audio is up loud enough. Oh, yeah. All right. That should be a little bit better for you to hear me now. So let me start off by saying that I'm noticing that a lot of people are clicking on the link for this class at like 8 and 9 in the morning. I'm not sure what's going on there, what you're looking for, but when you click that link, it actually tries to start a class session and it creates a recording. And part of the reason I'm delayed in putting recordings out in the announcements is because I've got 15 different recordings where people have clicked the class link. This class doesn't start until 10 a.m. So if you're trying to reach me for office hours, the link is just below. There are two different links. So be sure that you're clicking the correct one. In fact, about 30 seconds ago, I got a pop-up on my computer saying somebody just joined the office hours link. Well, office hours ended at 10 a.m. So you have to make sure you're using the correct link. The link for class is for Tuesday and Thursday at 10. And the link for virtual office hours starts at 9 a.m. So be sure you're using the right link, because I mean, I can't be in two Zooms simultaneously on my computer. So you have to be using the correct link, right? And I would hate for you to be sitting in the office hours thinking that's the class link, or vice versa, right? So pay attention to the information that you have and use the appropriate links. Okay. So last week we met on Tuesday and Thursday. We did a quick, well, I did a quick, let me say that, rundown of the Canvas course so that you would know how to find what you need. And then you had some assignments that you had to get completed by originally Saturday, but then I adjusted the due date and gave a little more time because, you know, I was getting messages from students saying that they just got their registration fixed or whatever. So I wanted to be, be fair and allow them to have time. So actually, the week one assignments didn't close until 11:59 p.m. last night. So now they're officially closed, and I will be scoring your submissions, if you did them this week, and get your scores posted for you. Okay. Any questions about that?
No, ma'am.
Okay. So let me go ahead and go into the weekly overviews, because remember, the weekly overviews is where you find all of the relevant course materials and assignments for the week, for each week. Okay. And so I'm going to click on the Nature of Science overview link. And so you see the first thing that we have there are the objectives for this material. You can see that we focus heavily on the scientific method in this portion of the materials. We look at the relationship between science and technology. We'll be looking at the metric system, the units and prefixes. And then you'll have some simple problems to solve relating to derived properties, namely volume and density. Okay, so take a quick look at the activities that you have on your plate. Okay, so for this week, you have a light load, if you want to think of it that way. You have a discussion to complete on the nature of science. And don't worry, the assignment level will increase. It's just that, well, I mean, I can't give you, here's the way I operate, so you understand that. I don't give a homework, a problem set, I should say, until after I've covered the material and you've had a chance to ask questions about it. And typically I have you do a discussion related to the material so you can kind of get your feet wet before you turn in a problem set. Okay, so there's a little bit staggered, right? So next week you'll actually have a problem set, which is, well, I guess all of it's homework because you're working from, outside of campus. But next week you'll have your first problem set that's due, but it will be related to this material, because again, problem sets are delayed by 1 week so that you have time to digest the material before you have to do it, right? And so under this Nature of Science overview, you can see that there are lots of resources available to you. There's notes and videos, some sample density problems, because we'll be looking at that. But you know, I always like to give you a variety of resources that you can utilize while you're trying to get through the material. Now, on the bottom here, you see supplemental notes. Those are typically the notes that I cover in class. What I'm going to do, because we only meet 1 hour and 15 minutes on Tuesday and Thursdays, I'm going to hit the high points of those notes on today. And then on Thursday, I'll do a quick and dirty review of the major concepts, and then we'll kind of look at some sample problems. Okay, so that's kind of how I'm going to operate, given the you know, the time factor. And of course, you know, if you have questions along the way, please stop me. Okay, please stop me. Okay, let me stop the share just for a second. I apologize. I should have turned on my video. I don't always do that when I'm in other meetings, but I'd like to, you know, for you to have some sense of my presence besides my picture. All right, so let me take a look at these notes. Again, when it says supplemental, those are typically notes that I will rely on. The other notes and videos you are tasked to deal with. Okay, let me try to move this out of my way. There we go. All right. So one of the important things that I often key on in my notes is this whole how to study stuff, because I recognize that, you know, this is a science course. It has some unique challenges. And a lot of times students struggle because they don't quite know how to approach this material. And so I will harp on this on a, you know, periodically to kind of keep you honest about how you're approaching this material. You should be reading the assignment material regularly, preferably before our lecture. That way, if you have some questions that you've come up with as you move through the material, you can get your questions answered while we're in session. And, you know, of course, you can get them answered at any point if you reach out to me, but, you know, you'll have the opportunity to fill your questions while we're here together, right? I provide you with ample amounts of notes and materials, but nothing can take the place of you making your own notes and making this stuff personal, right? You know your learning style, you know what triggers your understanding better than anyone else. And so you should take the notes and information that I give you and add your own 2 cents worth, as we say, okay? You should definitely work the problems and answer the questions that I make available to you in the discussions and problem sets, because that increases your capability of dealing with this material and your understanding. You have discussions where you can bounce ideas off your classmates. You have a discussion relating to every topic that we cover, and there is a class questions forum that you can link to in every weekly overview if you have just questions in general. Of course, you know, you want to be reviewing the materials regularly. And then, of course, you know, I give a midterm and a final exam. So obviously that, you know, completing those will give you an idea of where you're at as well. Okay. Any questions on that? Because I want everybody to get off on the right foot, you know, on the good foot, right? Any questions?
No, ma'am.
Thank you. One thing I will say is I find after having done this well over 20-something years, that those students who make an honest effort to engage with me, that means responding in class, reaching out to me during office hours, emailing me or communicating with me when they have questions, those students typically do the best. Okay, so if you've got your camera off and you're doing something else, multitasking, as they say, and I understand that world, I live in it. I was just in 3 different webinars. You know, if you're doing that kind of thing, you're going to limit your ability to be successful. So I always tell students, talk to me. Tell me what's going on inside your head as we're going through this material, so that, you know, it doesn't become overwhelming. Okay. All right. So this body of material is pretty straightforward, because what it does is establishes the foundation for how we develop this this knowledge that we have of our physical environment. And we'll see the scientific method as one of those key tools that scientists use to increase our understanding and application of, you know, the body of knowledge we call science. And we'll look at the connections between science and technology, because that's pretty germane to how our understanding of our physical environment has increased. Now, you notice me using that word physical environment, and that's because you're in a physical science class, right? There are different ways to have knowing. There are different ways to explain the things that we see happening in our environment and in our universe. What we focus on in this class is the ways that we understand, ways and things that we understand about our physical, I like to say, scratch and sniff environment. Okay. And even that can be, you know, more focused and narrow, because we're only interested in certain aspects of our physical environment, right? And so, you know, one of the things that we harp on is this idea that nature has an order and some simplicity to it. You know, we might have to come up with complicated ways to explain it, but it's actually quite ordered and simple. Okay. And, you know, you have to understand the human progression in terms of the ways they formulated understanding. You know, I mean, if you look at human history, we didn't always approach things from the perspective that we could understand how things work, right? And so the body of knowledge that we call science, that way of understanding our environment is built on theories and laws that help us to understand the truths of nature, how nature behaves, right? And then, you know, what do we do with our understanding of those theories and laws? What kinds of applications do we make? So there we go, right there. We look at science consists of knowledge and application. And typically we call that knowledge our theories and laws, and that application lends itself to technology, right? And so science is broken down in terms of specific fields and disciplines like astronomy, chemistry, biology, geology, and physics. This course focuses on physics. This is not we do some limited kinds of astronomy, but not astronomy in the sense that we're going to go out stargazing and that kind of thing, and telescopes and so on and so forth. Although the telescope is one of my favorite instruments, because that can highlight the connection between science and technology, we'll not actually be doing astronomy to that degree in this course. Okay, but we'll things like gravity and the planets and stuff like that, we will touch on some of that. We don't do chemistry in here, biology or geology. So I tell students this class is designed to help you understand our scratch and sniff environment through introductory baby level physics with a sprinkling of astronomy on it. Okay. And it's important for you to understand that, because you need to know, you know, what you're working with in here, right? I mean, if you're going to go out and repair your vehicle, for example, you got to have the right tools. You got to know, you got to know what you're working with. And so I want you to know what you're working with in here. What is our perspective in here? Okay. And as I said, it's physics. Okay. Now, I know when I say physics, a lot of people are like, oh my goodness, I didn't know this was going to be a physics class. No worries, because we don't get into high level math at all in here. We keep it very basic. Okay. Simple math that I can model for you very easily. And you'll see that when we do some sample problems on Thursday. All right. And so what is this physics? So you see here, physics is like one of the most basic sciences. Some people will argue and say math is even more basic, but I like to think of math as a language, the language that, we speak in physics, right? And so, since science is very basic, physics is very basic, excuse me, it deals with things like energy, matter, space, and time, and how they interact. And that's really what we've been focusing on here, and so we got to understand, how do we get that information that helps us understand these things, okay? And so I always tell people, physicists want to know everything about everything. But I like those last two words in that first paragraph. It says what? We want to know everything about everything that can be measured and tested. That's the crux of physical science. That scratch and sniff, that's your measurement and testing. Okay. And so if everything is built on measurement and testing, we got to understand that world. We got to be able to speak that language. Okay. And so, because physics is very basic, those more, I like to say, complicated sciences like biology and chemistry are built on the fundamentals that we as physicists uncover and understand. So physics is like fundamental, and other sciences are built on it. Okay. So when I talk about applications of physics, that lends itself into technology. Okay. And they give you some great examples of some technology there. Things like heating, cooling, all of those things that we love, we have to take advantage of now, with in the summertime and the wintertime, and lighting and all those things. All of those applications came about because of the knowledge that we developed, the body of knowledge and understanding that we put together and call physics. All right. As I said, one of my favorite applications of physics is the telescope. If you think about over the course of human history, the telescopes that we've developed. So go back to the 1500s or so, or 1600s or so, and Galileo and those folk who were using these crude telescopes. Now, they did some incredible work with those crude instruments, but think of how basic they were. And now think about how our understanding, has grown, and that has lent itself into developing these very, very sophisticated telescopes, right? We have telescopes out there now that, can, I always tell folks, we got telescopes out there now that can fry eggs and bacon, right? But they are really incredible because they, you think about the progression. But see, as our knowledge increased, our ability to build more sophisticated telescopes increased. So this knowledge and technology, they kind of go together. We learn more, we develop greater technology, which helps us to learn more, right? Which helps us to develop better technology. So they work hand in hand. And then, there are some scientists who are only concerned with knowledge. They don't care what you use it for. we call those guys theoretical physicists. And then there are some who put that stuff to use, right? And we call them applied physicists. So how did we develop this body of knowledge that we call physical science? What's the process that we went through, right? I will tell all of you that physics and science in general is not devoid of aha moments or voila moments where we figured out something that we weren't necessarily looking for. But by and large, the growth of the body of knowledge that we call physics and physical science has grown, in small increments through this scientific endeavor that we call the scientific method that we'll look at in a little more detail. But the start of that whole thing is observation. Somebody sees something and they want to know more about it. And so they come up with ways to investigate, right? But the key is, the start is observation. So they observe, and from this set of observations, because we're not going to say absolutely based on one observations, right? But we got to have more than one observation, and then scientists can begin to process that, right? And so this whole observation, we have to understand there are some things that we can observe directly, and then there are some things that we can't observe directly, but we observe them indirectly through the interaction, right? And so to give some examples there, like we can observe the motion of the sun, but we can't necessarily observe directly atoms and molecules because our eyes aren't that refined. But we can measure pressure and volumes, for example, of gases and determine how those particular atoms and molecules are behaving, right? So direct observation and indirect observation. And then once we get beyond the observing, right, we may want to find a way to model a certain phenomena. Okay. So we can't see electrons, but we observe them indirectly. And so we can come up with a model that helps us to understand the behavior of those electrons. And one of the things that we do, especially in physics, especially at this level, given the complex nature of certain things, we try to model it as simply as possible. So in this class, you're welcome to the magical world of physics, where we have frictionless pulleys and massless chains and simple systems, right? We try to model things in a way that you can get the general idea of the behavior, but we don't have to deal with all the extra. Okay. And so once we get beyond the observing and the modeling and we begin to package the knowledge that we have about a certain phenomenon. And we can package that knowledge in different ways. One way of packaging knowledge is a theory. Notice I did not say of one way of guessing about what's going on, because we really don't know. I didn't say that at all. I said that a theory is a way to package what we do understand. See, that's the mistake most people make about scientific theory. They think a scientific theory is we really don't have an understanding of it at all. No, it's just the opposite. A theory is our way of packaging what we do know. Now, granted, there may be some things that we don't know, but a theory helps us to package what we do know. And you see there that is an explanation for patterns. Patterns, that S on the end is very important. because that tells us that a theory encompasses more than just one phenomena, right? Okay, so we're explaining patterns in nature, and it's supported by scientific evidence and verified through reproducible experiments. So we're not guessing. We're not guessing. A theory is a way of packaging what we do know through experimentation, observation and experimentation multiple times. I always tell folks, a theory is a very broad explanation that of a phenomena explained through observation and experimentation by a lot of different scientists from a lot of different perspectives, a lot of different disciplines. Okay. So for example, later on in this course, you're going to be looking at the Big Bang Theory, not the TV show, the Big Bang Theory that explains the beginning of our universe. And that theory has been supported by evidence from a lot of different experiments, a lot of different perspectives and scientists and disciplines, and all of that understanding packaged and supporting a general idea that our universe began with a bang. Okay. So a theory leaves out what we don't know and packages what we do know. And it's a big package, very broad, because it explains patterns. A scientific law, on the other hand, is a bit more specific because it describes a pattern, one. And it is also supported by scientific evidence through reproducible experiments. But it's focused on a single kind of a pattern, and we can express that utilizing a mathematical equation. That's why I say math is the language we speak in physics, because our explanation of certain phenomena often reduces to a mathematical equation. And they give the example of F equals ma. That's Newton's second law of motion. So specific and focused, whereas a theory is much broader. Okay. Now, that's what they said. Generally speaking, a law describes a single action, whereas a theory explains a group of related phenomena. Okay. And here's the thing that, to me, is most important about either of these, about all of this stuff that we call science. It is not set in stone. A lot of people think theories can change, but laws can't. Absolutely wrong. All of it can change. All of it can change. None of it is set in stone. As we get better explanations, we are obligated to revise theories and laws. Okay, so keep that in mind. None of this is set in stone. I always tell folks, what you came to this class to learn is the best understanding that we have right now of our scratch and sniff universe. The best that we have right now. Okay. So the scientific method. This is the process that allows us to have a systematic observation and experimentation of, to test a phenomena. Okay. All right. So this scientific method, again, it's not the only way, because some things that we understand about our physical environment have come about because, aha moments, but the scientific method is important because it allows us to be orderly. Okay. And so this, as they mentioned, this process typically begins with an observation and a question. And then the scientist researches the topic and then constructs a hypothesis. So a hypothesis, you can look at there are two definitions that I typically rely on. A hypothesis, number one, can be thought of as a testable prediction. That's the key for science. It has to be testable. The other definition that I rely on is this notion of an educated guess. If it's just a guess, that's opinion. But if it's an educated guess, based on all of the information that we currently have, this is what we think. And then we go check that, do testing. And the way we test our hypothesis is through an experiment. So an experiment, the scientific method, is an orderly way to do our investigation of a phenomenon. And an experiment is an orderly way to test a hypothesis that's part of that investigation. Okay. And more oftentimes than not, our hypothesis fails. And that's okay. People think you aren't doing science if your hypothesis doesn't fail. If your hypothesis is correct, you are doing science whether your hypothesis proves correct or incorrect. If it proves correct, you still have to go back and verify. If it proves incorrect, then you have to say, okay, what went wrong? Let's see how to modify things and go back at it. And so here are some steps that you can utilize for the scientific method. I provide these steps because you will have to utilize the scientific method to investigate a simple question of your own. And so to make sure that you have a reasonable set of steps to follow. Now, some textbooks will have them just a little bit differently. They might break out the experiment, in terms of analysis, results, conclusions. But the basic concept of the scientific method is represented in these steps. Okay, and I took this from the CK12 textbook as an example of the scientific method. So it says, when the Titanic sank, what happened to the water level on shore? That's an example of a question. Now, is somebody really going to investigate that? I doubt it, but just an example of a question, but it highlights some very important things that I want to focus on. So in order to approach that question, first, the scientist has to do some research. So read and synthesize all the information available on the sinking of the Titanic. And after that, then the scientist will formulate a hypothesis. Okay. And maybe they'll have to pick one of those, depending on the information that they have available. Okay. And then they're going to test that hypothesis. Now, the important thing about this, testing the hypothesis, that experiment, is how you manage that experiment and the resources that you have available. Okay. Because if you set up a terrible experiment, then most likely you're going to get terrible results. Garbage in, garbage out. And then also the experiment that you do will be influenced by the resources that you have available. I mean, because if you have unlimited bank, for example, you might commission the building of a boat that it replicates the Titanic. And then you wait and watch the North Atlantic until the conditions mimic those that were present when the Titanic sank. I don't know if you're gonna get any people to go on it though, but but you get the idea that the type of experiment that you do is affected by the resources, funding many times that you have available. And the technology that you have available, right? Maybe there are some experiments that we want to do, we can't do right now because we just don't have the technology. And the data, so once you've gathered data through your experiment process, you analyze it. And then out of that analysis, you form some conclusions about whether your hypothesis was correct, or do you need to do some further testing. Okay, so that's just a kind of a, that's crazy example of the scientific method, but I did it to highlight the steps involved. And the other thing that I will tell you is, we can't, when we're engaging in this scientific method, the scientific endeavor in general, we can't leave our ethics at the door, right? You have to remember at all times that there are human beings that are doing science, and human beings have some issues. And the issues that human beings have don't just miraculously disappear when they become, when they're doing science. They bring all that stuff with them, right? And you can look throughout the course of history and see times when, as human beings, we didn't do this science stuff right. We did it in an unethical, even inhumane, and sometimes downright evil way, right? And so I always tell students, that's why it's critical that you be scientifically literate, so that you can make decisions for yourself about the usefulness of the information that we call science. If you see a commercial on TV, if you have taken Avandia and died, it's probably too late then to worry about, the work research that they did and in the process that they followed to develop that medicine, because you did. But if you understand how to digest scientific information, then you might question whether it's smart for you to take Avandia, as an example. And then the last few pages of this talk about the historical roots of physics and so on and so forth. You can read that stuff. They mention, the early scientists like Aristotle, who started to bridge the gap between philosophy and science and science as we know it. And then you move on to classical physics, where we have this embedded way of kind of starting to question our environment. Galileo, Isaac Newton, one of the most important people that we're going to deal with in this course, are key in that during that era. And then modern physics, where we get into things like relativity, and then people like Albert Einstein and Bohr and Planck, and those folks become critical. Okay. All right. So let me pause here, stop my share, and ask if there are any questions at this point on anything that I've covered. Or
I have a question, but it's not about what you went over.
okay, so if it's a class question, like about the logistics of the class, let's just hold that to the end.
Okay.
Yeah. Tiffany, I'm sorry, I think you were unmuting.
I just said no, ma'am. I don't have any questions.
Okay, thank you very much. Zachary, I saw you unmute for a moment.
Yeah, I was just going to say no, ma'am.
Oh, thank you very much. Okay.
Thank you.
Well, so let me just ask, to kind of provoke a little bit of dialogue beyond no questions. Somebody tell me what comes to your mind when you think about this marriage between science and technology, or knowledge theory and application. Somebody give me their own example that they might be thinking of.
I mean, I feel like they go hand in hand.
Absolutely. So I gave the example of the telescope as my example of how we utilize our knowledge and technology, together. Somebody else give me a different example.
Solar power.
That's an example that I've never heard. That's pretty cool, right? Because we had to learn something about the sun before we could harness its energy, right?
And use it to benefit us.
That's correct. That's correct. Now that doesn't all. You point out a very important thing, to benefit us. We don't always make the smartest choices about what we're going to use our understanding for, right? Somebody give me an example of how we might have used our knowledge and used it to build technology that you're like, that wasn't smart. Somebody else.
Nuclear bombs.
Ooh, you hit the magic example, huh? It's like, why would you want to use your knowledge to build something that could kill us all, right? I feel like those nuclear bombs are like, it's like kind of like Thanos. You just wonder when somebody gonna snap their fingers, right? Anybody else want to share? All right. Well, I appreciate those of you that were brave enough and engaged enough to unmute and share with me. That always helps to make the class rich when we can have dialogue with each other. And so I look forward to, over the course of the semester, talking with more than just a few of you. Feel free to join the conversation, because that's what gives this class, makes this hour and 15 minutes useful to us, right? Is that we dialogue and share with one another. All right, so I'm going to go back to the course page now, and I'm going to go into the measurement notes. And again, I'm introducing this today. We'll do a quick and dirty review of this on Thursday, and then we'll look at some sample problems that utilize our understanding of measurement. Okay. So see, notice again, right there, again, it reminds you on how to study. So what we want to focus on in this material is our SI base units and prefixes. Okay. So as I mentioned to you, we're in a physical science class, and we focus on physical properties, physical quantities, and the key to those physical properties or quantities is that they can be measured or determined using other measurements, right? They're either base measurements or they're measurements derived from other properties, okay? And so in physical science, there are certain properties and quantities that we rely on to the point where we even have information on how you measure those specific properties and quantities. Now, what I mean by that is that, for example, a meter. What's a meter? There's a physical definition of a meter that specifies how you determine it, but we're not going to get into those kinds of definitions, right? We're more interested in utilizing a meter as opposed to how do you get a meter, okay? And so I always tell students, that's what this course is about. How, our understanding of physical properties and quantities in our environment. And for us to do that, we have to have measurement. Because as I mentioned before, there are other ways of describing our physical environment. You know, when you hear a beautiful poem like roses are red and violets are blue, well, they are definitely describing something in the physical environment. But the problem with that is that that language can be ambiguous, because I might look at the rose and say, it's not blue, that's purple. Or you might look at the rose and say, I don't think that's red. I think that's like deep orange. You see, and the problem with that type of description of our environment is that it's ambiguous and can be interpreted multiple ways. But when we move to a more quantitative and physical description of our environment based on measurement, then we reduce that ambiguity. And that, you know, things that aren't ambiguous anymore. We're being specific. And what makes it even more specific is that if we're all using the same system of units to express our measurement. Okay, so this whole business of units is to make our communication and understanding clear. Okay, because we can all measure something in our environment. If I say go measure the length of your house, well, if I don't say measure it in inches or measure it in kilometers, if I'm not specific, then you could measure it with anything. Okay, so this idea of units is designed to keep us all on the same page. All right, now in physical science, there are only certain physical properties that we deal with, and so that means we use units that are relevant for those physical properties. Okay, in physical science, there are 4 fundamental units that we rely on, and you're gonna have to make yourself a note on this one, because they say the fundamental properties are length, mass, time, and electric current. I agree, electric current is a fundamental property, but we don't deal with it in this class. Instead, we deal with the fundamental properties, length, mass, time, and temperature. Length, mass, time, and temperature. So to think of these fundamental properties as like fundamental characteristics that we want to know about something in our physical environment. We want to know its length. We want to know its mass. We want to know how much time between 2 particular events. We want to know the temperature involved. So those are things that we can measure. And when we measure those fundamental properties, length, mass, time, and temperature, we need fundamental units. And if we want fundamental units, we have to be specific about what unit system are we going to be using. Now, in physical science, we use the metric system, the SI system, System International. Okay, there's an English unit, and we still use it in the United States, but I'm going to, except for the sake of a practice, I'm going to rely on the metric system in this class. Okay. So here we go. Let me do this right here for you. Let me see if I can move this. Okay, so I'm going to put this up on the screen. Tell me if you can see it. Can you see that? Somebody?
Yes, ma'am.
Okay, so I'm just going to draw real quick. So length, mass, time, and so we don't get it confused, temperature. Okay, so for length, we use the meter. For mass, we use the kilogram. For time, we use the second. For temperature, we use Kelvin. Okay. Meter, kilogram, second, Kelvin. Length, mass, time, and temperature. These are the base properties. And these are, oh, we done. These are the base units. Okay. So sometimes you hear them referred to as fundamental properties or fundamental quantities. Okay, you have to forgive me. I have to and these are the base units. Okay. So the 4 base properties and the 4 base units, and this is the SI system. Or the metric system, as you probably have heard it referred to. Okay. So you might be thinking, 4 things? That's all we have to learn about in this class is 4 things? If all we had to learn about was 4 things, we'd be done today. I promise you. I said, give me 15 extra minutes and we're finished with this class and you could mark down your A and move on with your life, right? But it's not that simple. I said that there were 4 fundamental or base quantities and 4 fundamental or base units. But everything is not the base. Sometimes we have more than our base, multiples of, and sometimes when we measure, we have less than our base, fractions of. And so we have to have a way to express multiples of our base or fractions of our base. And so we utilize these metric prefixes. Metric prefixes. Let me see if I can zoom in on that a little bit more. There you go. And so this is a table of metric prefixes. Metric prefixes. And these metric prefixes utilize powers of 10. Powers of 10. Now, in this table, they give quite a few of them. We don't use anywhere near all of these. There are some that we'll use regularly in this class because of the level of the class that we're in. Centi, milli, kilo, mega. Those are pretty common. Do I need you to memorize these prefixes and their names, their abbreviations, and their powers of 10? No. What I need for you to do is commit right now that when you are solving problems or answering questions in this class, that you will use this table if you need it. Use the tool that I provided for you. I don't like the idea of memorization because once you leave this class, you will do a massive brain dump and you will not remember this stuff again. So if you commit to utilizing the tools that you have available, then even when you leave this class, you will know where to find what you need. Okay? So don't memorize things. Use the table that I provided. Okay? So what these metric prefixes represent are ways that we can make multiples of and fractions of our base properties and base units. Okay? So, you know, you can take any one of our properties and put one of these prefixes on it. And that allows us to communicate consistently. The nice thing about these prefixes is that because they're based on powers of 10, there is uniformity. So if we say a kilometer versus and a kilosecond, we know consistently we mean 1,000 of them. Okay. So that's what these prefixes do. They allow for consistent communication, uniformity, and they allow us to make multiples of or fractions of our bases. Okay. So now, oh wait, sorry, I didn't mean to do that. Now, this whole business of unit conversions, that's next week's material. We'll get to all of that stuff next week, that unit conversions. So what I am going to focus on Thursday, again, I'll do a quick review to kind of recap and refresh. And then we're going to look at the idea of derived properties and derived units. Okay. So I'm not going to jump into that because I want you to take some time and digest and focus on the things that we've covered today and come back with your questions, whether you email me or hold it till Thursday. And then we'll move forward. I like to chunk knowledge in a kind of a logical way. So I'm not going to start looking at this derived properties and units until Thursday, after you've had a chance to go and, put some thought to the stuff that I've given you. All right. So I'm going to stop share and conclude by asking, are there any questions?
No, ma'am.
No, ma'am.
Is there anything that any of you want to share with me?
Actually, I did have a question.
Yeah.
I kind of probably missed the first few things you said about the basics that we need. Will they be posted on Canvas?
The basics that you need for what?
When you was going over like the basic, I have the metric prefixes table, but I just wanted to make sure if I missed anything else.
I don't know, because I don't know at what point you joined the class. I couldn't tell you exactly what.
I joined at the beginning, but like
okay, yeah, then you're good.
But I was just making sure, that I didn't miss like anything besides the table, because I was writing it down.
No, you didn't. But if you want to have access to any of the notes that I covered, all you have to do is go in the weekly overview and look under required readings viewings.
All right, thank you.
And that and the whiteboard that I drew, I will make available to you and when I post a video for this. And I do apologize that I'm a little bit behind with posting the videos. And that's again because right now, sitting on my Zoom account, I have about 10 different recordings for this class because people hit the link before 9 o'clock. Like before class time. If you open the class link before class time, it creates a recording. So I've got I might turn that feature off so that it doesn't keep happening. But I'll sort through them and then I'll get these videos posted for you. Okay. Yeah. So even if you missed something, you could always go back and watch the recording. All right. So those of you who have me for lab class, I will see you at 11:30. If you have any other questions you want to ask me, I think someone had a question and I told them kind of hold it to the end. Please hang around. I'll be happy to answer your question.
You had answered it while you were going over the stuff in the weekly overview.
Okay. Glad I did that. if there's anything you think of and you want to answer to it, just reach out to me. I'm more than happy and available to answer your questions.
Okay.
All right, everybody. Well, I'll see you back here on Thursday morning, bright and early, 10 o'clock. Y'all have a good rest of your day.
Thank you, you too.
Thank you.